and today I'll be talking to you about stream processing, this time in telecommunications. I hope that most of you were at the bus talks this morning. It was really interesting. Mine is a bit complementary to what he told us about. So first let's have a few words about our domain. So most of the clients of TouK are mobile operators, one of the largest Polish operators, and this talk is no exception. So let's have a look at what data do we process within mobile operators, so especially in real-time fashion. So the first and most important ones are the events concerning calls, SMSs, and so on. Each time you make a call, there is some event generated. Some of them are technical, and some of them are even more important because these are the billing ones. How much will the operator charge you for this SMS, for this call, or for this network transfer? Especially now it's kind of tricky in the days of EU regulations. And also, there are a lot of data collected concerns with localization. Where are you, with which base transmitter station your connection is provided, and so on and so forth. And also, of course, from time to time, your account also changes. You can change tariff, you can run some additional services, and so on and so forth. So, in fact, there are quite a lot of these events. As for billing events and SMS events, for large Polish operators, it's like few thousand per sec, so not so large amount, but still quite large. And from localization data and network usage data, these can be pretty huge, depending on whether you collect data only concerning kind of static localization or data gathered when you make a phone call. And of course, the changes on accounts are pretty rare, just few per second, so they are not any kind of performance bottleneck. So what do we do with all these events? Today I'll be talking about two major use cases, and the first one is marketing. So first we want to, in the stream of data, for example from calls, we want to find interesting events. For example, you're running almost out of money on your prepaid account, or you're close to point of sales and we want to offer you the latest and greatest iPhone, I don't know, 13. And we want to detect those events for the right customer. So you have enough money, you've paid all of your invoice, and in the age of GDPR, of course, we want to really be sure that we have your consent to send you SMS. And then we want to send this notification immediately. If we detect that you're near point of sales or you are about to cross the border and we want to invite you to buy some kind of data package, it's no use if we send this message after a day or even after a few hours. Few seconds or few minutes should be enough, right? So this is important. And another use case, another domain, is with fraud detection. There are many ways that people do frauds in telco. One is frauds of premium usage. For example, you set up some fake accounts using fake documents, and then you make constant calls to, I don't know, Bahama Airlines or Palau, which cost you a fortune, and you're not willing to pay the bills. There are accounts that are only set up to send SMS spam messages, which is of course against all the regulations or your agreements with operators. And also there's a little bit more sophisticated cases like SIM cloning. You have one SIM card, but using some fancy techniques, you clone it, and you can use the same account in many places. So we want to know that, for example, this SIM card is kind of simultaneously in two different places. And also many other, and some of the most kind of tricky are SIM-box termination fraud, where people just make use of different interconnect charges for operators in different countries. So many cases. And what we want to do is we want to compute fastly and accurately aggregates. How many calls did you make in the last hour or two? How much did they cost? Also, where were you, for example, a few minutes ago? Because if suddenly in 5 minutes you move to a different country, then probably something is going on. And of course, we want to detect some suspicious transfers, either from account, either from phone, and so on and so forth, right? And what we do to them? Well, the basic thing is to send some alerts or reports to revenue assurance team. But in the cases when we are really sure that you are fraudulent, we can block your account instantly. This is This is kind of new option. We really don't want false positives, because if you block your account and you are a normal customer, probably you'll go away to some other operator. So the funny thing about mobile operators is that they already process all those information in the real time. And it's this big black box called billing system. Okay, so they process all those billing events in real time and really reliably. This is the core system. But because it's core system, nobody wants to touch it without good need, right? It's no use to do some kind of fast changing rules and try to put it in the billing system, because it's so core and important that nobody wants to touch it. On the other hand, there are warehouses, analytical system, Oracle, SAS, Greenplum, whatever you like. And then analysts can do some SQL jobs, some more elaborate analytical stuff, and they have easy access to the data. But the data comes there with significant delay. Few hours is okay, few days, well, it means you're out of luck. And also those systems are not really ready to do production kind of execution, production actions. They don't have such good SLAs as kind of business support system. They are for dealing with analytical queries, but you don't want them to send SMSs, block accounts, and so on. So this is the goal that we are trying to achieve. We want to process those data as fast as in billing system, but on the other hand, we want them to be as easily accessible for analysts or business people as within warehouse. So how do we want to do this? Let's have a look at our architecture. Well, nothing fancy, you may say. Bus in the morning presented kind of similar stuff. So on the left, you can see some sources of data. They can be files, TCP streams, many legacy systems in mobile operators. Then we push everything through Kafka to Flink with some strange stuff at the top. We enrich with some client profile data, and we put the stuff again to Kafka to have another databases, to account management systems, to block it, to SMS sending systems, and so on and so forth. So, not so many logos on the slide, but I want you to pay attention to two of them. One is Kafka. I hope that all of you know Kafka, because it's a really great piece of software. I want to talk about it more extensively, because I think it's de facto standard of messaging systems dealing with real-time data. About Apache Flink, it's equally great piece of software, but it's not so widely known. It's kind of competitor to Spark. A few years ago, when we've chosen Flink, it was really kind of the only solution that could meet our needs. Now, as we've heard also today, Spark is catching up quickly, but still Flink has many features that it's unique for it. So what are the features? It's very low latency, just a few seconds of processing or milliseconds. It can handle something called exactly one semantics and also massive state, and it has really nice, rich API, expressive. So why should we care about this exactly one semantics and massive state? What is it for? Well, actually, with this amount of data, we have to take some certain measures to process all this data accurately, because we're in firehose mode and we don't have access to transactions. This is from SQL Server, but I assure you, in Oracle database, with such traffic, it's also difficult to have transactions. So Flink has pretty elaborate mechanism and concepts to handle those things, both to achieve exactly one semantic, so which means that when during aggregate computation the server blows up and we want to return to previous state, it will be handled correctly, no missed events, no bad calculations. And also have mechanisms for dealing with out-of-order events, late events, watermarks, whatever you like. So I won't go into the details, because firstly, Buzz did it pretty well this morning, and I don't really have time for that. But if you are into the subject, then be assured that Flink can handle it. Okay? Now, let's look a bit on the API of Flink. So, We define some source with some kind of, I'll show you Scala code. With some source, we have some variable. Then we filter, for example, the call events that last more than 10 seconds. We map it just like in normal Scala code. Then we define that we want to process our stream with each event assigned a key that is a customer ID. Then we define again some window with duration of 2 hours. We define that within each window we want to calculate the total duration of the call, and then we put it into some random Kafka topic. So as you can see, this is pretty normal Scala code. Of course, much is going on under the hood. Much is going on under the hood, but it's pretty nice and expressive code. So what does the developer do when he or she writes the code? Puts it into the jar and send it to something called job manager, which is kind of Flink gateway. There's one job manager for Flink cluster, which is kind of more distributed system. And job manager communicates with worker nodes, in Flink nomenclature it's called task managers, and sends the data and says, okay, run me this job defined by developer in this jar with this code that I've shown you on the previous slides. And then the job manager assigns some free resources on the task managers to the job. Each node has certain kind of threads or slots, and job manager assigns resources, and then when the job is running, they are communicate with each other. Sometimes there are network transfers, sometimes not. Of course, Flink tries to optimize as much as possible, but it's not always possible, especially if you do some shuffling, changing of keys, and so on. And from time to time, the job, which is happily running on the task manager, sends some kind of snapshot data to job manager so that it can save it into some persistent storage like HDFS and S3 and FS and so on, so that when one of the server crashes, it can be restarted. Right? So, seems easy now, right? I hope so. But that's the first question. So, what should be our Flink job? How large should it be? Should we have one global job per whole cluster? Some people do that. Should it be one per area, one for fraud detection, one for marketing? Should we have one source, one job per Kafka topic, or one job per marketing campaign? And all these approaches are perfectly possible. We tried the last one, because you see there are two approaches that you can take with respect to defining Flink jobs. One is kind of called microservice approach. We have a lot of small jobs in Flink cluster. Each of them is processing events separately. And that when you want to change the job, you change only this one. All the other jobs are unaffected. They are separate kind of entities in Flink cluster. Of course, they may share Java process, so they are not separate that much, but still you can replace it one by one. On the other hand, you can try more kind of elaborate approach that is not so flexible, but it can spare you much resources. So you have one large job with additional configuration, and if you want to add some new processing rules, change it, you define some kind of separate stream of data. One is your normal call data, and another one is kind of control process. So then the job runs happily, but you provide it with some additional configuration. So this is more difficult, more tricky, but it can save you quite a lot of resources. So we have this former approach, and we have some problems. Like, for example, the amount of threads on one of our nodes is like this. Like, our service is pretty beefy, like 40 cores or 80, but still it's far too much. So there are some downsides, but one can live with them. So I started talking about some challenges that you encounter when you run Flink in production. Let's look a bit on others. So let's have a look at how do we provide Flink cluster with the data. So the tricky thing in our setup is that mobile operators are kind of in many cases examples of large enterprises that have systems that can be like 15, 20 years old, and they're really rock solid and nobody wants to change them. So there are many sources of events, like in files, in TCP dumps, in log files, in some different formats, and it's not so easy to ingest them. So our first idea how to ingest data into our system was just to use Flink connectors. Flink can eat data from Kafka, but it can also read data from files, from HTTP, JMS, TCP streams, whatever you like. But gradually we move to something different. First, to this setup when we have two Flink jobs, one for data ingestion and putting into Kafka, and another from reading to Kafka and do real processing. Why did we do this? Well, essentially, Flink has many connectors, sources, but some of them are better than the other. And if you want to achieve exactly one semantics, good testing properties, and so on, you're better off with Kafka than with anything else. So we wanted to separate the ingestion from real processing. And afterwards, slowly we are migrating to this concept. We have similar architectures for a few clients. With some of them, we are trying Apache NiFi with some Kafka Connect, but we are using separate tools for data ingestion from files or TCP sockets to Kafka, and then we only use Flink to do real stream processing. So why do we do this? Well, essentially, as I've said, Flink has many source connectors, but not all of them are of really high quality. So we wanted to have separation of concerns when we have one tool that is responsible for data ingestion is really good about it. For example, Apache NiFi or Kafka Connect, they do really good job of transferring data from various sources to Kafka, but nothing more. And then we also gain kind of easier observability, right? Because if something is wrong, we know where stuff broke. Was it with data ingestion or with Flink processing, right? If we have this separate Kafka topic, we know how to find the culprit. And there's also one more caveat with such, I would say, real-time ETLs defined in large enterprises, because we define something like real-time ETL, right? We take the raw data, we pass it through Kafka, and of course we have to do some translations, some data cleaning, and so on, because the data is really raw. But the trick is, in the mobile operator, they also have another pipeline, rock solid 20-year-old pipeline that's implemented in Bash or Python scripts that takes the same data, puts it into a file, do more or less the same cleaning, and puts it into the warehouse. So as you may guess, the problem is, are all these processes of cleaning and translating data the same? These are in 12 or 20-year-old Python scripts, and this is something that we wrote in Scala half a year ago. So we try the best to be the same, but hopefully at some point of time we will merge it into one pipeline, because now some discrepancies are of course possible, right? So this is the problem with data ingestion. Now let's have a quick look about what happens next, right? How do we send SMSs, block accounts, or send some kind of monitor events? And again, at first, at the level of proof of concept, we started with sending various things from Flink directly, because it was easy to set up, it was easy to do, but gradually we've moved to more architecture like this, right? So Flink, after processing, after detecting interesting events, sends them only to Kafka, to some intermediate command topic, and only after then additional components like Kafka Framework, like Kafka Connect, send them, for example, to HDFS for further processing with some kind of big data stuff, or there are some microservices with Akka, Spring, or whatever, to really integrate ourselves with SMS gateways, blocking the blocking APIs, and so on. And again, it's the example of the attitude that everything should be streamed through Kafka, because it gives us good decoupling. Every task is performed by the part of the system that does it's the best. It's much easier for failure handling, because Flink is good at preserving this exactly one semantics, but restarts of the job, for example, due to external system failures, are quite costly, right? Restarting all the state and so on, it's not so easy as just retrying the request. So it's better to have separate component that handles the integration with other systems, for example, with web services. And again, it also gives us better observability. It's easier to track some suspicious stuff, for example, that we don't send SMSs because there's lag on one or the other Kafka topics, right? So this architecture is a little bit more elaborate, but still it gives us many, I would say, benefits. Okay, so we've talked about data ingestion, data executions. Now let's have a look at the bottom of the picture. That's the enrichment, right? Because those data that comes from our sources are kind of raw data from real telco system. Probably we have the SIM card number, probably we'll have the phone number, customer number if we are lucky, but not, for example, which tariff does he use or did he pay his invoices in time, right? So in many cases, we want to enrich the data because before we are able to process them with some various customer data, which tariff does he use, what is his customer segment, maybe what's his name even, and with some historical data, for example, the amount of on his invoices in the last 1 or 2 months. And also, let's not forget about many additional dictionaries. For example, mobile operator can have as many as few thousand of tariffs of various sorts, and we want to know if it's prepaid, postpaid, mix, or whatever you want. So, how do we do it? Well, the first and most kind of easy and natural approach is just take the stream of data, take your Flink job, and for each event, ask, in this case, Redis service or Cassandra or database, what's this client data, and so on and so forth. So, of course, it's easy until you realize that you have a lot of data. And you have like 20K per second of events processed by few jobs. And imagine we process this with, 10 threads. That gives you like 2,000 per second, which gives you like 500 microseconds, which is half a millisecond. So for round trip to Redis, this is quite small amount of time. Of course, you will say, let's do it asynchronously. But the thing is that in stream processing frameworks, even if Flink, which is really capable of doing many great things, asynchronous data enrichment is not so easy. It's not so easy to get to do it stable. So there are other approaches. One of them is to take your raw data and have some pre-processing job that enriches the events only once, and have this kind of intermediate Kafka topic with the data enriched with some client data. This is quite nice approach, but it only works up to a certain level, because if you put the client profile with each of your events, then you'll quickly run out of network bandwidth and disk. So this approach is viable if you want to enrich data with few really important kind of attributes. Another approach is to take, again, raw data more or less, and then have some kind of separate stream of account updates. And basically for each of the jobs, for each of the slots, you would have a cache of internal to Flink of this customer information data. And again, this approach is pretty interesting, but with many small jobs, it's easy to get out of resources, and cache invalidation is not so easy task, and doing this join even in Flink is not so easy approach. So there are a few options of data enrichment. Each has its pros and cons, right? First, we have to remember that we have to process it pretty fast. It's hard to sustain, even if you have local Redis with your client profile cache. This latency is hard to sustain. And either in Flink or I think also in Apache Spark, it's not so easy surprisingly difficult to get async enrichment right without, for example, violating ordering of events and stuff like that. And if you want to cache data within each job in each node, it's also possible. It's also a viable alternative, especially for smaller data like dictionaries. But again, it's difficult to get right and can be pretty expensive in terms of resources. So we've talked about ingestion, execution, enrichment. Let's look about the Flink jobs themselves. Again, as I said, Flink is really performant framework, and it, well, I would say, didn't let us down in the last 2 years. However, there are some things that we have to remember. If we do only kind of stateless processing like filtering, enrichment, and so on, everything kind of usually more or less works without any problems. But once we process state, things are getting a bit more complicated. Because what kind of state do we want to have in our jobs? For example, we want to remember last location. Where was your last call compared to the current one? This is pretty easy because last call for one client is kind of well-defined state. But we also want to remember the total duration of your calls in last 4 hours, right? This is a bit more tricky because this last 4 hours is kind of time window that moves continuously. Even more tricky if you want to count, and this is quite often needed, if you want to compute the total unique numbers that the client called to see if you are just constantly calling your spouse because, I don't know, your quarter told you just our spam account that sends marketing SMSs without our consent. Right? And of course, we want to detect all those suspicious events that may come out of this immediately and not, for example, after, 2 hours. So in Flink, we have 2 or 3 ideas of windows. The 2 basic ones are tumbling windows. For example, when we compute the duration of your talks from the midnight to 2 o'clock and then from 2 o'clock to 4 o'clock and so on and so on. This is very good for kind of more real-time analytics, but not for fraud detection. For fraud detection, we'd rather use sliding windows, which are more capable of answering how many calls from this point in time to a few hours before you've made, right? But there are also some caveats with them, and we had to do some our own windowing mechanisms. But the biggest problem is skewed state in fraud detection use cases. Because think of it, for a normal user, how many calls would they make per day? Like 10, 20? To how many people? Like probably less than 20. Maybe if you have a lot of friends, maybe 30, 40. But for frauds, for real spammers, they would make, for example, 50,000 calls in a day to more than 10,000 unique numbers. And these are the cases that we want to detect, right? And it turns out that for each of these kind of fraudulent numbers, the state that we want to keep either in memory or on disk can reach megabytes. So in memory, we can easily run out of it, and we want to keep it on disk. It won't be so performant to serialize each time from disk to memory, many megabytes of memory. So again, there are a few options that you can try to consider. One of them is to enlarge the granularity of the windows. Because if we want to detect spammers, frankly speaking, we don't care if you made these 10,000 calls during 4 hours or 4 hours or 5 minutes, right? You're a spammer anyway. So this is good for some of these use cases. We can also decide to ignore your later calls. For example, if you reach, 1,000 of calls during 1 hour, we don't care about if you reach 5,000 or 10,000, you are a spammer anyway, we want to block you. But in this way, we lose quite a lot of data, although it's kind of simple mechanism. And more elaborate solution includes using probabilistic data structures. There are quite a few data structures that, maybe not quite a few, but at least there are some that let you compute some approximate, for example, number of elements in a set that use very small amounts of memory compared to what you would have to use when you just made a set in Scala on Java, right? And again, this is for many fraud use cases, it's enough, right? If you called 10,000 people in 4 hours, you're a spammer. If you called, I don't know, 9,990, you're also a spammer, right? So some small errors are okay, right? So, and in our project, we started using hyperlog structure, which is quite tricky algorithm. If you want to see some clever data algorithms, just go and read it. It's implemented in Java in many libraries, so we just used it in one of them in our Flink jobs, and it performs pretty well for us. So we've talked about all those stuff and all the logos that should be more or less known to you, but what the fuck is this? Sorry. You didn't see that logo, did you? So this is the tricky part because it deals with designing processes, right? Because the Flink API that I've shown you is pretty easy, expressive, nice DSL. But remember, who will be using it? It will be used by analysts, business people, people that know SQL, they know Excel, PowerPoint, they can write really elaborate queries, but they don't want to code in Scala. And especially they don't want to build this jar, use some bash scripts to deploy it and so on. And they don't know how to monitor and so on. So of course, one solution is to let us, developers, do it. But unfortunately, it's not so easy, especially in our setup. Because as I've said, we were just a small software house and our client is large enterprise. It has its own business units, analysts, IT team, ops, and so on. And there are barriers between both their teams and between us and them. And this is the biggest barrier because it's spent between different companies, right? We want to make money, they don't want to spend money. No matter how good your relations are, this is the fact, this is the chasm. So we want their analysts to be able to handle as many use cases as possible without asking us, developers from other company for assistance, right? And this is how our project was born. Because at first, we did a proof of concept of the solution that I described with Apache Flink, and the results are really good. The performance was skyrocketing, and the business case that they developed was really also okay. But then our client said, okay, so we've hard-coded these use cases. What if we want to change some thresholds for marketing stuff and so on? So we've said, okay, we'll give you this configuration file. You can change it. It's easy readable, and it will be deployed automatically. Oh, okay, this will do. But what if we want to add some conditions to this process? How will we do it? Properties files are not enough. So we've said, okay, so we write in this nice Scala language. You don't have to know it. But in separate files, you'll write using some user interface, some small pieces of this code. They look almost like SQL, and they will be deployed immediately. Is it okay? It should be enough. But your commercial competitors have this nice user interfaces when you can draw diagrams. Do you have something like that? So, of course, we answer, okay, we'll do it. We're capable of that, and we'll make it open source project, so we won't have to pay too much for that, and okay, do it. And this is how our project, currently it's open source project Nussknacker, is born. If you want to know what the hell is this, so the story is that Flink is developed in Berlin, Germany, and it has the squirrel in the logo. So Nussknacker is a German word that can be used for problems that are too hard for a real squirrel to deal with. Okay, so the name was invented by the owner of our company, so we're using it. If you like it, I have some stickers. So the problem that we really wanted to solve is to create some nice feedback cycle. First, these analysts, business people have their own warehouses, SaaS analytics and stuff like that, and they perform some queries to design some fraudulent cases. And then we want them to be able to implement this Flink job that will be first deployed in some kind of test cluster when they can see for example, for a few days if their assumptions weren't correct, and then deploy to production, again, by themselves, and gather some data to get a feedback and see if their assumptions were correct, right? So this is kind of a, well, holy grail of analytics. And the biggest problem was with that error. How to come from their SQL queries and so on to something that can be deployed in a real production system. So this is something that we aim to build. And while building that, we have three main assumptions. So the first assumption was that we won't get rid of coding, right? The definition of model of integration with outside systems will be still the job of the developers, right? If some external system, for example, with service management stuff changes, probably we have still to figure out how to call a web service and so on. This is the developer's job. No need for analysts to do that. And the second is that expressions for configuring the business rules or the aggregates and so on should be accessible for kind of semi-technical guys, right? People who know SQL, people who know Excel, but not necessarily the code. And the third, very important, is that we wanted to facilitate testing and prototyping because, as I've said, the analyst guys were really capable of doing many analytical queries and stuff and for designing prototypes, but they are not used to running anything with production. And up until now, the usual kind of output of their job was some Excel sheet, some presentation with pie charts and so on. But now we wanted them to be able to create real supporting systems that have appropriate SLAs and so on. Right? So the architecture is pretty simple, right? So first we, the developers, define a jar of model integration, some additional variables and so on and so on. We prepare a config file where the Kafka is located and where Zookeeper is and so on. And also create JSONs. And this JSON, each JSON with the jar and config files can be deployed to Flink clusters, separate job, and everybody is happy ever after. So, of course, the analysts don't create those JSONs describing Flink jobs with Notepad or even Notepad++, but with some kind of graphical user interface, right? This is something kind of, they say to us it's user-friendly enough for them, so so of course we believe them. As you can see, there's some kind of a toolbox and some block diagrams that describe how to handle, for example, this marketing case, right? So some of the nodes in toolbox are some generic stuff like filtering, splitting, and so on and so on. And some are prepared by us. And this is integration with external systems or some more elaborate sources of data. For example, some alerting system. And this is done in real normal Scala code. If you don't want to code Scala, you can also do it in Java if you really want to. And we defined what will be the parameters of this service. And then the user will just fill the parameters and write expressions. And for expression language, this is kind of funny part because we wanted to take something that compiles quickly, so Scala was out of question, of course. And we decided to use something that we knew that is Spring expression language. For those of you who know Spring, you know that Spring expression language is usually used for parsing configuration, but we use it in our Flink jobs. We can even type the expressions and do some basic completion. But the most amazing thing about this language is that we invoke those expressions kind of, I would say, probably in peak more than 200,000 times per second. And this language that was designed to handle configuration files somehow managed just to keep up with performance. So Spring is really kind of remarkable piece of software there. Of course, it's easily abused. If you look at this expression and say, I don't know what this means, you're absolutely right. You can write monstrous expressions which analysts can sometimes write, but they don't know how to use it. And the performance of it is, of course, far worse than expected. But for simple cases, this spell thing is quite enough. Right? You may, of course, wonder, why didn't we use SQL? Because, well, this is what the analysts are used for. And the one reason is that Flink didn't support SQL 2 years ago. It has some pretty decent SQL support at the moment, but then it didn't have, so we didn't use it. But there's also some deeper reason, because think about this SQL. when you run it on your database, you can filter on this free condition, and you get an answer matches or doesn't match. But in our real-time jobs, sometimes analysts want to have some more detailed knowledge which of the conditions, the tariff condition, duration condition, or charge condition, caused this particular event to be filtered out, right? So when you have all these conditions in these separate block diagrams, it's much more easy to track the execution, right? Although, of course, SQL language is far more kind of declarative, high level, and nice. But for them, it's enough. And another thing you may ask is, so how do we define windows, aggregates, and so on? And the question is that we didn't want to give users full power to do that, because we figured out that if we make our kind of user interface to complete that you can do anything, its complexity and the difficulty to use it will grow exponentially. So what we did was to let developers create some predefined aggregates, which are written code in normal Flink API, more or less like I've shown you before. And here the business user, the analyst, only configure it. So for example, there are some few predefined types of windows, and the user only says, okay, this window should be calculated with respect to customer ID or phone number, and it should last for 4 hours, and it should calculate the sum of these fields, right? But the definition of window is kind of hidden. So it's simpler, but usually expressive enough for them. Right, so now the process was designed in this tool, of course it's safe and so on. Some audit is done, and now they want to run it. So to avoid some further questions, we do run it in production. We have some around 50 jobs running in production, Flink jobs. Our largest diagrams created with this tool are that large. I think this is again some kind of misuse. It shouldn't be that large, but if you give users power, yeah, they can create really crazy things. And at peak, our jobs combined run about a bit more than 1,000 requests per second, right? So it's kind of decent throughput, and all is handled by our project. So important thing is to make user test their code, because once they are able to deploy it in production, well, from our other client, I have this quote. So because testing is difficult, first let's run it into production, and then maybe if it's okay, we'll deploy it to test. So of course we don't want them to do this. So we have some testing facilities. The first one is sandbox testing. So this is how normal job works. Take some data from Kafka, put it through Flink, enrich data, and put some to some outside systems. And what we do with kind of sandbox testing is that we take the test data, for example, from file. We use the same production-ready client profile. So we ask Redis to provide customer data. And then we don't send real SMSs, we only collect mocked invocations, right? And the other nice feature that is possible because we use Kafka is that we can generate test data based on some real events. For example, we can take 10 last events from Kafka and put it into the file. And then user can see how the events were processed, dig down, what were the outcomes of all the expressions, how was it filtered out. And then when he's more or less ready with some sandbox testing that he wants to have some better use case, he would go to kind of user acceptance test environment. Because if with this architecture with Kafka and Flink, it's pretty easy to set up. This is our kind of production cluster. And then on our user acceptance test, we have smaller one. This one is capable at the production one of running, 50 jobs, and this about 5 or 10. That's easy. That's enough for testing what the analysts are currently working on. And they have the same Redis customer profile data. For example, clone of Redis cluster and so on. And Kafka makes it really easy to replicate the real stream of production events to this user acceptance cluster. And of course, we save the generated events. We don't send real SMSs, but send it somewhere else to the analysis, right? So they can deploy this process in this user acceptance cluster, let it run for a few days and see what happens. Because many things will happen. First, they want to analyze how the job is doing, and with each of the conditions, especially with the more important one with business events, filtering and so on, we put the outputs both to warehouse and to our Elastic cluster. So the first one gives more possibilities in terms of difficult analytical queries, and the Elasticsearch cluster lets user have faster access to data, but without too many possibilities of advanced joins and so on, right? Because many different things may happen, and when you let users define complex queries, complex segregate, they can overuse it and not be aware that much resources is needed and so on. So we want to monitor that. And with each Flink job, we have some additional Grafana dashboard automatically prepared, so they can see some kind of key metrics like latency, throughput, are there any errors, and we can also define alerts if some job misbehaves, right? Because we also have some technical monitoring with Grafana that lets us handle both the failures of our system and also failures of source system if some events are not coming our way. Right, so this is more or less all I have to tell about our project. And as I said, it's open source project, so it's production ready. Feel free to use it, but don't expect, at the moment at least, really great documentation. There are also some documentation, some quick start, but you know, this is kind of constant work in progress, and we're working really hard. So the main points that I want for you to remember was, first, if you want to do stream processing, use Kafka. It's really de facto standard. There are some other tools, like now appearing, like one from Alibaba, one from Pravega, but Kafka is really de facto standard. It really works pretty well. The second thing is that you should aim to be able to create this nice feedback cycle from analysis through testing, functional testing, integration testing, and production without the need for development. This is kind of a holy grail of this whole business. And this next thing is that you should start small with simple processes, stateless processes, with filtering, then only add enrichment, and only if you are capable of doing those things, try to do aggregations, because stateful stream processing is quite tricky, and you have to be really sure to know what you're doing to avoid some difficult performance problems. And also, to let your business users feel safe, start safe with generating monitoring events only after you are set and it's okay. You can start to send SMSs, which is kind of delicate subject nowadays. And if your business really kind of trusts you, you can do some more invasive stuff like blocking accounts, right? So that you can build trust within your business users, right? And remember about having proper testing setup. With this architecture, it's really easy to replicate the data to user acceptance cluster when you can test them safely and monitor them. And if you want to see how to create Flink jobs with user interface, you can go to our site. It's on GitHub and look at Nussknacker. I didn't have too much time for a demo, but there are some Docker demos, and I can show you one if you want to after the talk. Okay, this is more or less how you reach me. If you have any questions, please do have, although I think we're running out of time.
So we have a few times for questions.
Thank you for a good presentation.
Thank you.
Question about usage, say, role of Grafana in the monitoring. On which data you use monitor?
So the most important metrics are kind of throughput through the process, because we have some metrics that show us the health of the whole cluster. For example, are there any problems with checkpoint mechanism with Flink, some standard Kafka metrics, but we also have separate kind of based on tag values dashboard for each process. When we monitor first the throughput, then the latency, how large is lack of the topic in Kafka cluster, and also, so yeah, throughput and latency are the most important one. Also, the rate of events that were filtered out on each steps of process. This is kind of more like KPI for the business, so that they know if they should tweak some conditions, and also some more technical stuff, like for example, if we invoke external services, are there any errors and stuff like that. But for more complex stuff, we push many things, especially after first filtering, where the amount of events is smaller. We push as much as we can to Elasticsearch, so that we can have better vision. But at the beginning, you can't put everything to Elastic, but the amount of data is too large.
Thank you.
And one more question.
Hello, thank you. Interesting talk, really. I think I'm gonna sell it in the office. My question is,
please do.
how prioritized is development of this thingy? You said it's open source. Do you accept pull requests? Do you do something else? I mean, is it active? Because I contributed to many open source projects, and sometimes people just don't have time because it's not their main project, it's pet project and stuff. Do you prioritize development of this thing?
So you see, the thing is that we develop this tool as an open source project, but it's currently used and kind of developed for our largest or few customers that use it. So we're developing it constantly. Of course, we have to share our time between kind of closed source integrations for them and support of their systems and development of Nussknacker. But yeah, we're eager to accept contributions and so on. We don't have to very large team, just like 2 or 3 people, but still the development is kind of, yeah.
Thank you.
Okay. So thank you very much. One more time. Enjoy the last talks of the conference.